Yucatan Peninsula, 600 AD, Mayan architects coated every exterior wall with burned limestone plaster. On clear nights, those surfaces became colder than the surrounding air. No compressor, no electricity, no cooling system of any kind. They were throwing heat directly into outer space through a gap in the atmosphere. Stanford University documented this effect in 2014, a surface reaching 4.9 degrees below ambient air temperature at solar noon. The $185.9 billion cooling industry never put that discovery on a contractor's price list. By the end of this video, you will discover exactly why and how to do it yourself. Subscribe so you never miss what the cooling industry hopes stays buried. Every civilization that confronted extreme heat without mechanical cooling independently arrived at the same surface solution. White mineral coating applied to exterior walls and roofs facing the sun, made from whatever local source of calcium carbonate the landscape provided. The result in every case was interior temperatures held measurably below exterior air temperature with no active cooling at all. The Moorish engineers who built the Pueblos Blancos of Al-Andalus understood this without calculus or spectroscopy. Beginning with the Moorish settlement of the Iberian Peninsula in 711 AD, architects across what is now Andalusia applied cal, hydrated lime dissolved in water, to exterior walls as standard construction practice. The resulting white finish achieved solar reflectance above 85%, while simultaneously maintaining the high infrared emittance required for radiative heat loss into the atmospheric window. Thermal performance surveys of traditional Pueblo Blanco structures conducted by the University of Seville's Escuela Técnica Superior de Arquitectura and published in 2003 documented interior temperatures in whitewashed lime plaster buildings, averaging 8 to 10 degrees Celsius below simultaneously measured exterior air temperatures during peak summer hours, averaging 8 to 10 degrees Celsius below simultaneously measured exterior air temperatures during peak summer hours. Frigiliana, Casares, Mijas, Vejer de la Frontera. These villages have maintained that performance continuously for 900 years. Through the annual application of the same material, their Moorish founders first spread on those walls in the 8th century. 7,000 kilometers south, the Nubian people of the Upper Nile had arrived at the same conclusion at least 2,000 years earlier. The archaeological record of Nubian domestic architecture documents white mineral-coated mud brick construction from the 8th century BCE onward. During the Oriental Institute of the University of Chicago's Nubian expedition of 1960 to 1968, conducted before the rising waters of Lake Nasser submerged much of the region. Field researchers documented continuous lime and gypsum exterior plaster traditions across villages from Aswan south to the Fourth Cataract. In a climate where summer temperatures in the Nile Valley regularly exceed 45 degrees Celsius, survey measurements confirmed interior temperature differentials of 10 to 14 degrees Celsius below exterior air in traditionally constructed whitewashed structures. The raw materials, limestone and desert gypsum, were available within walking distance of every building site. The material cost was zero. In the United States, the lime whitewash tradition arrived with European settlement and survived in continuous agricultural use through the early 20th century. The United States Department of Agriculture's Farmers Bulletin No. 474, published in 1915 under the title Warm Whitewash and Cold Water Paints, documented the thermal performance of lime whitewash on agricultural structures across the American Southeast and Midwest. Field measurements cited in the bulletin recorded interior temperature differentials of 8 to 12 degrees Fahrenheit below exterior in whitewashed barns, compared to unpainted structures under identical conditions. The USDA distributed this bulletin to farming households across the country for 3 decades. Then petroleum-based paint manufacturing scaled through the 1940s, and the industry that replaced lime whitewash had no financial interest in documenting what it had displaced. Different continents, different centuries, different minerals, identical physics. Modern physics calls this phenomenon radiative cooling, specifically passive daytime radiative cooling, when it achieves temperatures below ambient air and direct sunlight. The mechanism operates through a property of the Earth's atmosphere that most people have never been told about. The atmosphere absorbs and re-emits most wavelengths of thermal radiation, which is why the greenhouse effect works, and why the planet retains heat. But in the wavelength band between 8 and 13 micrometers, the atmosphere is almost completely transparent. It doesn't absorb, it doesn't re-emit. Thermal radiation in this band travels from a surface on the ground through the entire thickness of the atmosphere and exits into outer space, where the effective background temperature is approximately 3 Kelvin, and exits into outer space, where the effective background temperature is approximately 3 Kelvin. Physicists call this the atmospheric transparency window. Every physical object above absolute zero emits thermal radiation. The rate and efficiency of that emission depends on the object's temperature and its emissivity. how close to a perfect emitter it behaves in the relevant wavelength band. A surface with emissivity above 0.90 in the 8 to 13 micrometer band emits heat through the atmospheric window, at a rate that, under clear sky conditions, exceeds the rate at which it absorbs solar radiation. Surface temperature drops below air temperature. This is not a theoretical prediction. It is a measured physical result. The Stanford University research team published their 2014 results in Nature after developing a 7-layer photonic structure engineered specifically to maximize emittance in the atmospheric window. Their surface achieved 4.9 degrees Celsius below ambient at solar noon in direct sunlight. In 2017, the same research group published results in Nature Energy documenting a fluid cooling system using the same principle, delivering 93 watts of cooling power per square meter with zero electricity input, comparable to a standard residential ceiling fan running on electrical power. Stanford subsequently spun out a commercial company, SkyCool Systems, to commercialize radiative cooling panels for large-scale applications. SkyCool's installed systems operate today in commercial buildings in California and Texas. A standard exterior mineral or elastomeric paint with high infrared emittance achieves 70 to 80% of the theoretical maximum radiative cooling effect documented in the Stanford research. No photonic engineering required, no specialized laboratory equipment. A surface any homeowner can apply in an afternoon with a roller. So why is there not a high emittance radiative cooling coating on every new American home? The answer has nothing to do with the physics. It has everything to do with who gets paid when you run your air conditioning. The global HVAC market was valued at $185.9 billion in 2024. Carrier Global Corporation, the world's largest manufacturer of residential and commercial cooling systems, reported revenues of $22.0 billion that year. Trane Technologies, Lennox International, Daikin Industries, each generates revenue through an identical economic structure, equipment requiring installation, maintenance contracts running annually, refrigerant recharges recurring on a 3 to 5 year cycle, compressor replacements arriving at year 12 to 15, and a full unit replacement at year 18 to 20. The average American household spends between $400 and $1,000 per year on residential cooling energy alone. Across a 30-year period, that figure reaches $12,000 to $30,000 per household, paid monthly to utility companies and periodically to equipment manufacturers, on a replacement cycle that never terminates. A high-emittance radiative cooling surface applied to a residential roof eliminates 50 to 90% of peak cooling load. One application event, a service life measured in decades, no compressor, no refrigerant, no annual service contract, no replacement event at year 15, zero recurring revenue for any manufacturer of cooling equipment. The building energy standard governing new residential construction across the United States is ASHRAE Standard 90.1, published and maintained by the American Society of Heating, Refrigerating, and Air Conditioning Engineers. ASHRAE's technical committees include staff representatives from Carrier, Trane, Lennox, and Daikin. Cool roof performance within ASHRAE 90.1 is evaluated using the Solar Reflectance Index, a metric measuring how well a surface reflects solar radiation in the visible and near-infrared spectrum. The standard assigns no separate compliance credit for thermal emittance in the 8 to 13 micrometer atmospheric window, the precise mechanism responsible for subambient radiative cooling. A surface that reflects 85% of solar radiation and a surface that both reflects solar radiation and radiates 93 watts of cooling power per square meter directly into space receive identical compliance credit under the current standard. The more effective technology is invisible to the code. The Cool Roof Rating Council, the organization that certifies roofing product performance ratings referenced in both ASHRAE 90.1 and the International Energy Conservation Code, was founded in 1998. Its founding members included GAF Materials Corporation, Owens Corning Roofing, and Certainteed Corporation. All three manufacture traditional asphalt, shingle, and roofing products that meet existing solar reflectance index thresholds without modification. None produces a competing high-emittance radiative cooling coating. None had any financial incentive to create a compliance pathway for a technology that reduces the cooling load to the point where mechanical cooling becomes optional. Germany's National Energy Code evaluates thermal emittance independently of solar reflectance, providing a full compliance pathway for radiative cooling performance. The Netherlands does the same. Both countries have operated under these standards since 2007, but you do not need anyone's permission to understand the physics. Here's exactly how to do it yourself. Before you purchase a single liter of coating, 3 pieces of information determine whether you achieve the sub-ambient cooling documented in the Stanford research. Or simply apply an expensive white paint. First, your roof substrate condition. High emittance coatings applied to cracked, degraded, or contaminated surfaces lose 30 to 50% of their documented emittance performance through adhesion failure and thermal bridging at surface defects. Clean and repair the substrate completely before applying anything. Second, your climate zone. Radiative cooling performs at full documented capacity under clear sky conditions because cloud cover reduces the atmospheric window's effective transparency. The American Southwest, Interior West, and California's Central Valley achieve the full sub-ambient effect. The Pacific Northwest and Gulf Coast, with persistent summer humidity and cloud cover, see reduced sub-ambient performance but still benefit substantially from high solar reflectance. Adjust your performance expectations before installation based on your local annual cloud cover percentage, not the Stanford laboratory results from Stanford's dry California climate. Third, permit requirements. Applying a coating to an existing roof surface requires no permit in most residential jurisdictions in the United States. If you are re-roofing and applying the coating as part of a new roof assembly, contact your local building department for applicable IECC or Energy Star Cool roof requirements. A correctly specified high-emittance coating will meet or exceed those requirements in every case. Select a product that meets both of the following performance thresholds simultaneously: solar reflectance of 0.85 or higher, thermal emittance of 0.90 or higher. Both numbers must appear on a Cool Roof Rating Council product rating certificate, which manufacturers are required to publish for any product making a cool roof performance claim. Do not accept a product that lists only one figure. Do not substitute standard white exterior latex paint. Most exterior latex products achieve solar reflectance between 0.65 and 0.75 and thermal emittance between 0.85 and 0.88. These numbers perform adequately, but fall below the threshold required for documented subambient cooling. You need both numbers above their respective thresholds simultaneously to access the full atmospheric window effect. Elastomeric roof coatings in the 100% acrylic category and silicone-based roof coating systems consistently meet both thresholds. Manufacturers, including the Henry Company, Rust-Oleum's roof restoration coating line, and Duralast Industrial Coatings, produce verified products with published CRRC ratings meeting both specifications. Coverage rates run between 1.0 and 1.5 gallons per 100 square feet for a two-coat application. A standard 1,500 square foot residential roof requires 15 to 22 gallons of material, total cost of $180 to $330 at current retail pricing. Application requires a roller, a brush for edges and penetrations, and an afternoon. No licensed contractor required. Apply to the roof surface first. Roof surface temperatures in direct summer sun reach 60 to 80 degrees Celsius on a standard asphalt shingle. The coating eliminates the majority of that thermal load before it conducts into the building structure. Wall application on south and west-facing surfaces is additive performance, not a substitute for roof application. Reapplication every 5 to 7 years is non-negotiable. Emittance performance in the atmospheric window band degrades with sustained UV exposure and surface contamination buildup. A coating applied once and left without maintenance drops below the sub-ambient threshold within a decade and functions only as a standard reflective roof after that point, delivering perhaps 20% of the documented cooling benefit it achieved when fresh. Set the reapplication date on installation day. The reapplication material cost is identical to the original installation. For homeowners in high humidity climates where cloud cover limits subambient performance, a white silicate mineral paint manufactured to DIN N12878 standards, sold under the Keem brand in the United States, achieves solar reflectance of 0.88 and thermal emittance of 0.91 while delivering a vapor-permeable, mold-resistant surface that outperforms standard acrylic coatings in humid conditions. It delivers 75 to 80% of the full radiative cooling benefit with a service life exceeding 20 years before reapplication. Applied correctly to a standard 1,500 square foot residential roof, this coating reduces cooling energy consumption by 50 to 90% measurably from the first full summer. No electricity, no moving parts, no service window. When the power fails during a summer heat emergency, as it did for more than 4 million Texas households in June 2023 when a heat dome pushed the grid to its breaking point, a home-running mechanical air conditioning goes from 72 degrees to 95 degrees within hours, and stays there until the utility restores power. A home with a high emittance coating on its roof actively loses heat to outer space from the moment the sky clears. No grid connection required, no refrigerant charge required. No licensed technician available or unavailable on a Tuesday afternoon in August. The cooling industry spent $185.9 billion last year. It spent none of it ensuring that Aswath Rahman's 2014 paper became something on your contractor's price list. The Nubian builders of the Upper Nile applied this physics to mud brick walls in the 8th century BCE. The Moorish engineers of Andalusia maintained it through 900 continuous years of annual whitewashing. Stanford University measured it in a laboratory in 2014 and published the result in Nature. The atmospheric window is still open. The cold of outer space is still there at 3 Kelvin. The physics work today exactly as they worked the day the first Uxmal architect burned their first load of limestone. Now you know not just why this was buried, but exactly how to do it yourself. Subscribe if you loved this guide and watch the next video appearing on your screen right now.